All right, here we go. We finished up the constructing cones exploration yesterday on page 220.
Yeah.
So we're moving on. And this problem is that we're doing next is brought up so often, you've done it so many times already. However, would you look in your exercises at the diagrams that they have there for you to practice this little thing I'm going to show you? It's on page 227. The boxes that you are going to make are quite a bit more complex.
Yeah.
So hopefully you can adjust to that because I'm doing the simple one.
No.
Okay. Here we go. All right, so page 221, the classic box problem. Here's the deal. An open topped box is to be made by cutting congruent squares of side length X from the corners of a 20 by 25 sheet of tin and bent up the sides. How large should the squares be to make the box hold as much as possible? And what is the resulting volume? You've seen this before, right? At least twice before. So what we need to maximize is the volume. And so we need a volume formula for a box. It's pretty straightforward. I mean, initially, just in general, it's what? Yep. And in the box that we're making, it comes from a flat sheet of paper, much like our cone came from a flat circle yesterday. And we're going to cut squares out of it. It has to be squares, otherwise it folds up funny. It's got to be squares out of the corners. And these will be gone now. We'll throw them away. We've got this strange looking thing, and we are going to fold it or bend it along these dotted lines. Fold it up, and that's pretty crappy dotted line. Fold it up like this and like this to make a box that you see there pictured on your page, right? And it was initially 25 by 20. So how long is this from here to here?
X.
25 minus
2x.
2x, one from each end.
Yep.
And this distance from here to here now is
20 minus 2x.
20 minus 2x, because it was 20 before and we took x off of each end. So now that we've got our generalized deal right here, how long will this box be?
25 minus 2x.
How wide will it be?
20 minus 2x.
How tall will it be?
X.
Easy peasy, right?
Yep.
A lot better than yesterday, right? Wasn't that coming? Okay, so once we have that, and your calculator doesn't care what form it's in, so you don't even have to FOIL that out and distribute the x. You don't have to do any of that. However, the most important part of doing these problems is always overlooked at this point because everybody grabs the machine. What's the most important part that I tried to reiterate to you yesterday?
Window. Think about it.
Yeah, think about your domain. What's the very biggest, what's the very smallest x can be in this diagram? 0, which means you're not making a box. That's still the smallest it can be. What's the very most it can be?
Can't be
Just
more than
10.
20.
Just
10.
10. Because you can't, on the short side, you can't cut in any more than 10. You can on the long side, but that's not it. The biggest you can cut in is on the short side, and you can only cut in halfway. That'd be the x max. So if you think about that domain, decide what x could possibly be at the very most, and then don't look at the part of the graph that's outside that domain. So it won't make any sense, and it'll just confuse you. So go to the window. I'm going to go from 0 to 10. Okay, now I want you to think of something else with me for just a minute before we go on. This distance from here to here is likely 1 or 2 digit number. Probably 2 digit, but smaller than 25, right? Well, this number here that goes from here to here, will that likely be a 2 digit or 1 digit number?
1.
I'm thinking it's probably more likely to be a 2 digit that's, this one. You think? And when you get the height of it, this distance right here, which will be the height, you suppose that'll be a 2 or 1 digit? 1. So when you multiply a 2 digit number by a smaller 2 digit number by another number, what size number do you get?
Probably 100,000.
Thousands? Hundreds? What do you think? 10,000s?
I think it's hundreds.
High hundreds, because look, our 2 digit number here is less than 25. It's likely to be either in the very low 20s or upper teens, right? this thing. This thing will be in the low teens. Take a high teen minus a low teen, or times a low teen, you're gonna get, okay, and then multiply by another number, you might get into low thousands possibly. What I'm trying to get you to consider is what this volume is gonna turn out to be, so you can set your window decent without experimenting too much. So I'm gonna let my, because I wanna see my y-axis, I'm gonna let my minimum be negative 100, and I'm gonna let my maximum be 1,000. And I'm gonna count by hundreds. I may be way off, but I should be able to see something. Oh, I haven't put the thing in yet. It's graphing the thing I had in before. It's not working at all.
No.
Okay, so I gotta put this thing in it. 25 minus 2x, 20 minus 2x.
Well, that's what I got.
Yeah, it fills up the screen pretty well. It's obviously not symmetric. This is what you should be getting, something like that when you consider, oh, glare, okay? So it fills up the screen pretty well. We want to find the maximum, do that. Okay, here's what we get for the answer to this. I mean, when we find the maximum value, this guy right here where the cursor's blinking right there, that maximum value, according to my calculator, to the nearest thousandth is 3.681. And the y value is
820.528.
thank you, 820.528. This is what our calculator gives us, but you, as the doer of the problem, have to be able to interpret what that means. Who would like to try?
I would like to try.
Good.
So the cutout X needs to be 3.68 inches. And then that will produce a volume of 820 inches cubed.
And that will be the, that's just a volume. That will be the maximum volume.
Yeah.
Yeah. If we had to do this just with calculus and without the calculator, how would you? I'm not going to do it, but how would you? If you had to use calculus to find these numbers.
Derive
Derive that and get a V prime. And then what?
graph that.
Well, I don't want to graph that on. I don't use the grapher at all.
Oh, yeah.
You would, whatever that is, you would set it equal to 0. It'll be a polynomial, right? This is a cubed polynomial. This would be a quadratic. So it's just a polynomial, which means there's no consideration of division by 0. I mean, no critical values that are produced from undefined. And so we would solve this quadratic and we would get some x values. I bet you one would be positive and one negative, and I'll bet you this would be the positive.
Yeah.
And then you would plug it into this to find the volume that was produced from it. Does that make sense?
So that's just an alternate way to do it.
That's the calculus way to do it. But again, like we're diminishing that in favor of the calculator and in favor of the modeling step, which is this, the model. That's the most important part of this section. On your test, I will not take away your calculator. So if you have only the calculator method in your mind, that's fine. I bet this is a calculus class. So I wanted to talk about how we would do it if we use the derivative and how we would get these numbers from it. You would find the derivative, set it equal to 0, give you 2 x's because it'll be quadratic. This would be one of them. The other one's probably negative, so we would decide in favor of this one. And then we would plug that into here to get this. Yeah? You follow me? I hope so. All right. So that is example 3. Example 4, I would rather you didn't turn the page. The whole presentation of the problem for example 4 is at the bottom of page 221. And I don't want you looking at the solution. I want you to help me come up with it by paying attention closely to the modeling step. Go ahead and read it. Then I will read it, and then we will tackle it. It says you've been asked to design a 1-liter oil can shaped like a right circular cylinder. In other words, a can. A 1-liter oil can. Question is, what dimensions will use the least material to produce this can? So what are the dimensions of a can? What dimensions do we need?
Top and bottom and side.
We need the radius
Yeah.
and
The height.
the height. That's it. We need the radius and height. Those will be the dimensions, but we need those, the radius and the height of the can that will use the least material and still hold a liter of fluid.
I feel like you're gonna need to use an inequality then.
What's that?
You need to use an inequality.
No.
I can see how that would make sense. I appreciate
The
it.
can, I'll make it a little taller so it looks, I don't know. But there's the can that we're gonna try to produce. And we need this, and we need this. And what are we going to try to optimize here in this problem?
Material used.
Material used, and how do we want to optimize it? We want to find the least amount of material necessary to hold a liter in a can. What's the one thing they gave us that we know? And the volume is what? I like that. I like whoever said 1,000 milliliters. It is 1 liter. But even the milliliters, I really don't want the milliliters. I want it because, see, when I figure out how much material it's going to take, it's going to be in square something. Right now, I've got cubic, but I don't see the cube there at all. I don't see anything cubed. So I'm going to need to remember my metric and convert that to cubic things because I'm going to have to take those cubic things and make them square things to produce the material. Cubic what? Centimeters. How many? 1,000. That you have to remember your metric system and your science experiences well enough to understand. But we need volume expressed this way in centimeters of some kind so that we can express our area in centimeters of some kind. So that's the first thing. Okay, so we have our volume. We want surface area. Looks to me like we're going to need a couple of formulas. What's the formula for volume of a cylinder? Does anybody remember?
Higher square is.
What's the surface area? By the way, when I write this, this is one variable. One variable. Surface area is equal to what? Does anybody recall?
2 pi r plus.
Have you turned the page or are you remembering? You better be remembering.
2 pi r.
2 pi r h plus
2 pi r squared.
Yeah, 2 pi r squared. These are the two circles at the top and the bottom. These are the can lids, the bottom and the top. This is the rectangle that makes up the cylinder.
Okay.
Do I need to show you?
If you unroll it. Yeah. Yeah. It's just like a piece of paper.
Would you like me to demonstrate that for you?
Yes.
Yeah? You got it? Anybody else need to know why this is a rectangle?
Why does it have a 2 on it?
Circumference, 2 pi r, is the length of it. The height is the height of the can.
Yep, we're good.
Does that make sense? Circumference times the height, because when you roll up a piece of paper, the circumference is the length of it when you open it back up.
Right.
You everybody following? Okay. So this is surface area, this is volume, and this is the only thing we know. See how the modeling is coming together? They gave us something about volume, you need a volume formula. They asked us something about surface area, you need a surface area formula. And now we've got to morph these things together so that they will be in terms of one or the other variables, either R or H. And as we go to the morphing part, it will become obvious which one we want to use. So this one I know, it's got an R and an H in it. I mean, I know the volume. This one's got an R and an H in it in several places, but I don't know that. Do you understand that indicates we want to solve this for either R or H and plug it in? That's a standard move. Do you want to solve for R or solve for H?
H.
Because we don't want a square root.
Yeah.
See how it becomes clear which one you want to solve for? Okay, so I get 1,000 over pi r squared, and that's equal to H. And then we replace H over there. It only occurs in one place. That's another nice thing. It only occurs in one spot. We'll replace H with this. See what we've got. So surface area is going to be 2 pi times, oops, not yet, R times 1,000 over pi r squared plus 2 pi r squared. We got a little bit of cleanup to do here a little bit. So I'm going to take this pi out here and one of these r's and multiply that by 2. So I get 2,000 over r. That was nice. That was a quick simplification. Plus 2 pi r squared, and that's my surface area. And think about what we're going to do now. I mean, we've got that simplified as much as possible. We're going to, what are we going to do with this? We're going to graph it. And we want to consider the window, the domain. And here we just got to think a little bit. We gotta estimate. I know you guys are all typing that in. Would you please listen for just a minute? This thing's got to hold a liter. Have you got a feel for how big a liter is? You got an idea? If you don't have a feel for liter, it's just about, but not quite the size of a quart. Got an idea? And we want to fit that into a can that's measured in centimeters. Its dimensions are measured in centimeters, and in particular, the radius of such a can. What do you think the radius will be in centimeters to hold a liter? I mean, it could be like this. It could be really, and have a radius like this, or it could be pretty squatty, like a tuna fish can, only spread out. But still, it's not going to be, to maximize the volume, it's not going to be like this and this tall. So, give me an idea. How big do you think the radius might be? 10 centimeters. That's as long as a decimeter, which you can see up here, about right from here to here. That would make it, if we did that, the radius was that long, that would make the can about this big around, probably bigger than that, pretty squatty. Anyway, 10 seems reasonable to me, but you need to consider that. So I'm going to go with 0 to 10 again. What do you, and the height will be, think about that. What's the range of it? Oh, yeah, it's not the height, it's the volume. No, the surface area. That is much, much more difficult to estimate. Surface area, everybody always gets that wrong. So what do you want to use for, just give me an idea for surface area.
2,500.
Oh my God. All right, 2,500, I'll go with that. Negative 100, I'm still going to, so I can see my y-axis. And now I'm ready to type it in. It's going to be 2,000 divided by x plus 2.
That's good. Okay.
X squared.
Oh, yeah.
Do you get something like this?
Yeah.
Does this, will we be able to do what we want to do with this?
Yeah.
Because we are
Find the minimum.
minimizing, yes. A lot of people, if they do not think about the y values here, a lot of people will miss this because what they've chosen for y is too short and they won't see anything. So if you are minimizing, learn that. If you're minimizing and you don't set your y's high enough to see it, get those y maxes way up there so that you can see it. A lot of people don't. So find the minimum.
Oh, gosh. Well, let's see, shall we?
Find the minimum. This is what it should look like. There's your minimum. And the answer that we get, again, I'm going to write this up here and ask for an interpretation. 5.419. And y equals 553.581. Okay. Who wants a shot at interpreting what we've got here? Or are we ready to interpret?
So like the X would be what the radius is to minimize the material used, and the Y would be the
Least
minimum
amount of material.
surface area.
What would this be measured in?
Centimeters.
And this?
Centimeters squared.
Oh no.
Okay, so what you're saying is to use the absolute minimum material, I would need,
A radius of 5.419.
and that would give me a material usage of,
553.
so about 554 square centimeters you're gonna need to make this can. And that's the minimum amount. We could make a can, we could make all kinds of cans. That's the minimum material you would need to accomplish the 6 centimeter goal for volume, right? But the question also asked, and what are the dimensions of the can?
Yeah, you'd find the thing like.
How do we do that?
Plug in the R's.
So I'm going to change this to R, because that's what we've got is R. And I'm going to change this to surface area, because that's the minimum surface area. What I need now is the other dimension, which is H. Plug it in here, right here.
Yeah.
You already got h solved for. So it would be 1,000 divided by pi times that thing squared. And remember, that's sitting in your X mailbox. But don't forget those.
That's what I wrote.
So on my home screen, once I've quit, I'm going to find h by taking 1,000 divided by parenthesis pi. And I'm just going to use x because x is this. That was the last thing my calculator came up with. So I'm going to just say x squared. And we get 10.8839. Okay, so now full interpretation here would be a can with a radius of 5.4 and a height of 10.8. Ooh, did you hear the words? We'll use minimum material of 553.581 cubic square centimeters. But I want you to look at these two numbers. What do you notice?
Yeah, they're half.
Radius is half the height, which means the diameter is equal to the height.
Yeah.
That's what we call a square cylinder. And it is the most efficient. It is as far across as it is tall, and that's the most efficient cylinder, meaning the most you can get for the material you use is a square cylinder, if you will.
Does that mean it's like the same height as the, so it's like,
It's as wide this way as it is tall.
oh, that probably looks kind of funky.
It does. I want to talk to you about that for just a minute. Minimizing surface area, minimizing material used is sometimes the goal until someone actually sees the mock-up of the can.
Right.
And then they go, we're not doing that because it looks stupid. People don't like it. It's too big for your hands. It's too short. It does not pour well. If it's an oil can, something like that. And so they'll look at that and go, that's not going to sell. People don't like that. How do they know they don't like it? Because I don't like it.
Yeah.
The guy who's making the cans, he goes, no, we got to go a little taller, a little skinnier so that it looks a little more attractive. And then he starts giving dimensions and he'll say, I want it to be about that big and about that tall so that it's about maybe, 1.618 taller than it is across. That is the most appealing shape. Called the golden rectangle. That's not what the manager of the company will say because he doesn't know that. But you might, as the designer and the mathematician, speak.
How do they do it when the can tapers off at the top when you're trying to find volume? Because this can curves up at the top, but they have to figure that out differently, on the bottom.
Yep. It's because they fit together.
Yep.
And they can be stacked, which is exactly the reason why people think that cups are tapered like this because it's prettier. It's not, so they can stack.
Yep.
There's reasons for these things. And just so you know, pull up that Red Bull can again. There's Red Bull can, and when you get a tall Red Bull can, one that holds as much as my Rockstar can, Rockstar's got a different shape than the Red Bull. It's got a slightly different shape, it's a little bit wider. And you get a Red Bull can that holds as much as this, it will be taller and skinnier.
Is that a 16 or a 20?
It's a 16. But what I'm saying is this, it's kind of a strange thing, and I don't know where Red Bull is based, but I think that they go with the skinnier can because it's more appealing because skinny means fit.
They're out of Germany.
Yeah, they're.
Out of Germany. But that's why this guy is in California. Okay? And it's very, very strange, but what they've come up with is that we value shorter or wider. That's what our athletic heroes look like. Football players are wider and shorter, stockier, beefier. People in Europe, what are their athletic heroes? Soccer players. Much more. I don't know about much more, but when they're on the field, they look more fit than our football players a lot of times, and usually are. I mean, I look at football players; they got their big old white pads on, but they've also got fat coming out. Wow, the big guys that are hard to push around. Still, we value that. We don't want to be pushed around. But in Europe, where they value their soccer teams, their football teams, they tend to be taller, skinnier. I'm not kidding. That's what people value these guys do these studies, these qualitative studies, and find what the best, I mean, they ask people, you like this can or that can better? Americans usually will choose this. Europeans will usually choose that. It's becoming more and more and more that people will choose that because football is becoming more, I don't want to use the word acceptable, but people are valuing it more. So we see these kinds of cans. It's very strange. And so this operation right here is a really fun, cool math thing to do, but it is not practical. In either case, it's not practical. If you want the most efficient container, in other words, if you want to use the absolute least material, you guys listen? The absolute least material to get the very most volume inside, it's always a sphere. So if your objective is to minimize volume or minimize material and maximize volume that it will hold, you would put everything in a sphere, which is highly impractical because you'd have to build little like egg cartons to put it on the shelf. And as soon as you picked it up, put it in your grocery cart, they'd all roll towards you as soon as you took off, and they'd roll around your house unless you had those. That would be dumb. So even a sphere though, even a sphere that has a flat bottom and a flat top for opening and for sitting, so it doesn't roll around, is fine. Nobody likes those. They're it's hard to get your mouth at the top before it starts tipping and dribbling down the side of your chin.
So if they ship things en masse, just like for like bulk production, would they use something like this? Because nobody cares what it looks like. If you're just shipping material.
No, probably not, because people still care whether they can put it on a shelf and leave it there for a while.
Yeah.
You know, it's just not appealing. They're just hard to hold. They're hard to do. I mean, you can put them like this. And you get a lot of bolts in there, but you got to pop the top off and you got to fish the ones out of the bottom and dump it out.
I mean, like if you have like it's like a really big container, you need to bulk ship something.
Oh, yes, except for the sphere will hold more than anything else, but all the space wasted when you're putting a bunch of spheres together is not economical either. So there's all kinds of things you got to consider. Anyways, we are done with that example. Are you okay with that? See how that one worked out? This one was a little easier to put together than the cone one, right?
Yeah.
Two more things. Examples from economics. Page 223. This one's going to be kind of interesting for those of you who like business and money and the capitalist idea of things. First of all, we need some definitions, and these won't be hard for you guys because you've been around for a while. These are really hard for freshmen. They don't know what's going on. But you guys probably know this. Can you tell me what revenue, cost, and profit are and how they are related? I need definitions and a relationship. Don't give me the relationship first.
I can do it.
Okay, tell me what you know.
Okay, so
Speak loud enough for the people on the video.
the revenue is the amount of money that's made selling a product, not the money you get to keep, because the profit is how much, okay, I guess I should do the cost next. That's how much it costs to produce a product.
Okay.
And then the profit is the revenue minus the cost. So that's how much you get actually.
Okay, so you're saying the cost is the amount of money it takes to produce the product. Can you tell me what's might be involved in cost?
Well, if you're like manufacturing something, you have the overhead costs, like the factory, the machines that it takes to make it, and then the material used to make the actual product. And then with labor, you have to pay for labor. So
Anything else?
probably one, yeah.
Taxes,
Tax.
mortgage, insurance,
Electrical bills.
electric, yeah, that's the overhead. Overhead, when they say overhead, they literally mean overhead, the lights and the things, then the machinery, or the energy it takes to run the machinery. So overhead costs, you're right. You got taxes, mortgage, insurance. Why insurance? Because if your employees get hurt, you gotta be able to cover them. If your product fails and causes someone to get hurt, or just plain fails, you don't meet your commitments, you have to have insurance. There's all kinds of costs. So tell me again, what's revenue?
That's the amount, like, when you sell it, that's the amount you get back for something.
So
But not the one you get.
It's what you bring in.
Yeah.
Yeah. It's the amount of money in your cash drawer at the end of the day. Okay? And then you said, what's the relationship?
Well, the relationship's the profit, because that's how much. you
Okay,
actually
tell me how
get.
those three things are related.
It's revenue minus cost.
Revenue minus cost equals profit. Because revenue is the amount of pile of money you've got at the end of the day. You take that pile of money and you pay your taxes and your insurance and your people and your materials bill and your overhead. And then the little pile that's left is profit. And that's for you as the business owner to take home. is one of the reasons, and it's only one, in my opinion, the reason why inflation is going, the reason why we're experiencing inflation is because a lot of the business owners like McDonald's, they're having to pay more for the materials that they get into the store to make burgers with. They're not gonna eat that difference. If it costs them more, they'll charge you more, so that their profit margin stays the same. So we're the ones that get hit with it. Okay. Let's talk about then, now that we understand those three relationships, they're gonna use RC and P, amazing, revenue, cost, and profit for these things, and they're all gonna be functions of X. Functions of X. What the heck is X gonna be in the context of this scenario? What's X gonna be?
Amount of things made.
Yep, exactly. The number of items produced. If you are a car manufacturer, then X is the number of cars that roll off your assembly line. If you are, we're only gonna sell one item because this could get really complex really fast. So if we're doing only Big Mac sales at McDonald's, then Big Mac, the number of Big Macs sold is X. It's the number of items produced and sold. Not just produced, because now you've got inventory costs. We're not gonna bring that into it either. It's just, you're gonna produce these and you're gonna sell every one of them to keep things simple. Got it? X is the number sold, or produced and sold. Do you remember what I told you in the past what marginals are?
Just said derivative.
Mathematically, it's the derivative. So when they ask you to find marginal profit, you will find the profit function and take its derivative. And that equation, whatever you get, is marginal profit equation. What it really means conceptually, marginals are the cost or the amount of money to do the next one. Revenue means the amount of revenue I will get for selling the next item. Cost, how much will it cost me to produce the next item? Profit, how much profit will I make by selling the next item? Marginals are an approximation for how much it will do, how much there will be for the next one done. It's either cost, made, sold, whatever. All right, so the Theorem 6 says this. Maximum profit, that's what we're doing in this section, is maximizing and minimizing things. Maximum profit, if any, and there may not be one, but if there is one, will occur when the production level, the X, the size of X, at a production level where marginal revenue equals marginal cost. That is a mouthful. Remind me again how, not marginals, but just regular old cost, revenue, and profit are related.
Profit minus cost equals revenue.
Okay, can you give it to me in another way with profit by itself?
Profit
Oh, did you already?
minus
You did. Okay. Is what?
R minus C.
Revenue minus cost. Sorry, you were right. You said it right. Okay. So listen to what the theorem says. Maximum profit. So if I want to maximize profit and it occurs at the marginals of some kind, I need the marginal profit. This is not hard, by the way. What is marginal profit?
The derivative.
The derivative. Good. So in this case, it would be,
R profit.
Yeah.
Minus C.
so this is in a general way. This is X is the cost of, or the production value, the production amount. Okay. So if I want to maximize profit, and knowing what you know about derivatives, what do I need to do next to find a place to look for maximum profit? Set your marginal profit equal to 0. In other words, this. Marginal profit, or the derivative of profit, set it equal to 0. So I'm setting it equal to 0, like this. Are you with me?
Wait, but why are we doing this?
Because that'll be a maximum.
Because we're trying to find a maximum. When you find the derivative and set it equal to 0, you're maximizing. I did that pretty badly. You're going, you can just let the marginal profit be 0. No, what we're saying is, here's the marginal profit with the derivative. We're going to set it equal to 0 to find places to look for maximum. Okay? And what that means is that R prime equals C prime. We're looking for places where that happens, because all I did is kick the negative C prime over here. Does that make sense to you? You see the math? Now let me read it again. Maximum profit occurs at a production level at which marginal revenue equals marginal cost.
there.
That's what that says. Everybody clear? So the proof was not that hard. Now, at the bottom of page 223, there is a graph there, and he gives a brief explanation, which makes reasonably good sense. The blurb there to the left, you look at the graph while I read this. Richard, relax. It's okay. The graph of a typical cost function. Which color is cost? Blue. So look at that. The graph of a typical cost function starts concave down and later turns concave up. I'm not going to explain why that is. It crosses the revenue curve at the break-even point B. In other words, when your cost, the amount you're putting out to make a product, and your revenue, the amount you're bringing in, it's called the break-even point. It means you're not making anything, but you're also not losing anything. Does that make sense? The break-even point. Okay, it crosses the revenue curve at the break-even point B. To the left of B, the company operates at a loss. Can you see that?
Yep.
Because cost is above revenue in that region. Okay, so they're operating at a loss. To the right, the company operates at a profit. The maximum profit occurring where R prime equals C prime. Further to the right, cost exceeds revenue, perhaps because of a combination of market saturation. You know what that is? It means everybody's got one. Nobody wants to buy it anymore. That's why you build in obsolescence. You build it to break so people will have to buy it again. Crap. Make me so mad. Poor quality products. So that you'll have to buy it again. Okay? It could have to do with market saturation and rising labor, perhaps, if you've got the Biden administration operating things. And material costs, they're going up because of the Biden administration. Thank you. Okay. And production levels become unprofitable again there when they cross again. Okay. So you want to keep your production levels somewhere between B and where that next cross point is, but you'd like to find the place in the middle that's going to make you the absolute most. And it occurs when the tangent line on the cost curve is parallel, because that's the same derivative, as the parallel line, or the line parallel to it on the revenue curve. So you want to find, it's going to happen between B and that second cross point. We want to find the very best place for it to happen, where the slopes are the same of these two curves. Notice that the slopes are the same before that as well. So that if we were actually doing this graph, and we actually had these curves, if we set the revenue, the marginal revenue equal to the marginal cost, and solve it, we'll get two critical values. One will occur before B, and one will occur between B and the next cross point. Which one do you want? The one between B and the next cross point. So once you find critical values, you have to plug them back into the original revenue and cost and choose the one where revenue exceeds cost. Otherwise, you're going to find the place that operating at the maximum loss. That's not good. So you have to do some checking. All right, let's look at example 5. It says, suppose that R of X equals 9X. That's revenue, right? What is X again?
X is the product sold.
X is the number of items. X is the number of items. So revenue, what are we asking for each item? $9. $9. And it's a line with a slope of 9. Oh, that line. Okay. It's a line whose slope is 9. And that makes good sense if you're not going to change your price. Your revenue curve will just be linear, right? Because every item you sell, $9. You're not going to change your price at all anywhere. Your revenue curve will be a line, which is the case here. The cost curve, that's based on a whole bunch of other things. And it's a cube function in this one. I'm not going to try to figure out where that came from. Not in this class. It says X represents thousands of units. It's important that you read that and understand that and keep that in your brain. It's thousands. X is in thousands. Okay. Is there a production level that maximizes profit? And if there is, what is it? There's not guaranteed to be one, but we're going to try it. So revenue. R of X is 9X. Cost is
X to the third minus 6X squared plus 15X.
Sorry,
15X.
minus.
Plus.
Okay. So in order to use this thing that we've just convinced ourselves is true, we need the marginals for each. So I have R prime, and that's just 9. I have C prime, and that's
3X squared.
Yep.
Minus 12X plus 15.
Okay, and I want to set those two things equal to each other. Because of this theorem that we just proved right here. Everybody clear what we're doing? Since it's quadratic, and the way we handle quadratics is to get everything on the side where the positive term or the squared term is positive, I'm going to kick that 9 over, set it equal to 0. And I now have 4 options. I could factor it, which it's going to do. I could factor it. I could quadratic formula it. Those are your pencil paper, analytical. Or I could graph it and find the zeros, or I could polyroot find it. I can see you all opting for polyroot. Go ahead. I'm not. I'm gonna do the grunt work here. Don't tell me what it is. See if you agree with me when I'm done. Ooh, it's not gonna.
Quadratic formula.
Yeah, I don't know that. I'm giving up. All right, somebody who's already gone through the process. What do we get for roots for this?
0.58578.
0.58578.
I guess 579.
Okay.
And you handle it.
You got about 3.414.
Okay, so these are X values. These are values where we have to look for a for maximizing our profit. So what you got to do now is
So you plug both those back into the originals of both, and then
decide where revenue exceeds cost.
Right.
Now, if you have these guys graphed right here, if you have them graphed, you could just ask the calculator what those values are. Otherwise, you're going to have to plug it in.
okay.
So if I plug this guy in right here into 9, what do I get for him? I get an R of X here of what?
5.272.
And what do I get for cost? It's kind of uglier. This is a place. This is a location of production, a value of production for which cost is more than revenue. As a matter of fact, cost is more than revenue. This is the maximum where their difference is the maximum, and this is a location, a production level of maximum loss. Plug that one in now and tell me what I get for R.
Uh, 30.7278.
Very clear that this is going to maximize your profit because that's where revenue exceeds cost at a critical value means that's where revenue exceeds cost at its greatest gap.
So
So this is maximum profit here.
So wouldn't it always be the higher one because of the way that the profit and cost curves act with each other?
Depends. Depends on, sometimes cost curves are not concave down first, sometimes they're concave up. In which case you'd be going like this.
Right.
So, but you should check it out. I mean, if you want to give evidence or whatever, if you're on a multiple choice test and you want to take that risk, that's okay. You can do that. You're probably right. I'd check it out. At least graph the curves and look at those points and see if you can tell which one exceeds the other. I mean, that'd be another thing. You could visually check it by graphing this curve and see, look at where these points are and see if cost is above profit or the other way around. I mean, cost is above revenue. You can see that too, rather than actually find the values. Okay, so how many should we produce to maximize profit then? What's the answer to the question?
3.14.
Yes, and you will miss that.
Oh,
1,000.
Should be 3414. That's how many. That's how many items you should produce. Because these X's are in thousands. It says so in the words, and you need to pay attention to that. So I take this, but I realize this is it. I got to move it over 3 and just lop off the rest because I can't make a piece of an item. Okay? You all right on that, Boston? Okay, one more thing. Having to do with economics again. This one might not be quite as obvious, but I'm gonna show you. And it will become obvious to you as we work through it together. What we're gonna do now, because we maximize profit with this process, we are now going to try to minimize our cost. That is also desirable as a company owner, right? Minimize your cost. So this is an optimization section. We know how to maximize our profit now, or what to look for, and now we're gonna try to minimize our cost. And here's what it says. Theorem 7 says, a production level, meaning an X level, if any, may not occur, at which average cost is smallest, is a level at which average cost equals marginal cost. That may not make sense to you, economically speaking, and they got you going, I don't even know where that comes from for sure. But listen to what it says. It says average cost is smallest. So we're talking about minimizing average cost, and it will occur where that average cost equals marginal cost. That's what we're saying. What is the average cost? If this is my cost function, C of X, it's a function of how many I produce, then what would the average cost be? This is the total cost of producing X items. What would average cost be?
C of X over X.
Yeah, very good. Divided by X. That's average cost. Does that make sense to you? If not, I need to explain it.
Please explain.
This is the total, that right there represents the total cost of producing X items. Total cost, total out-of-pocket money. Divide that by how many we produce, that's the average cost per item. That make sense? Okay, because you need to be able to understand that part of it. And we want to, this is our average cost, and we wish to minimize it, which means in order to find places to look for a minimum, I need to derive it. So I'm going to change this to C sub of X sub average. So C prime of X sub average, in other words, the derivative of C prime. I'm looking for places where the average, this guy right here, average cost is minimized. I need to find the derivative and set it equal to 0, right? Well, then I need to derive this side, and I need to use the quotient rule, which is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. You agree?
Yep.
All right. So now that I have the derivative of average cost, I set it equal to 0 to find places where I can look for minimums, right? Is that what you do, mathematically speaking? A fraction will only be 0 when its numerator and its denominator is not. We are not going to consider the fact that we can minimize our cost by producing nothing. That's not something we're going to consider. So X is not going to be allowed to be 0 because that's dumb. We just shut down the company and walk away. And we certainly minimized our cost. That's dumb. So we're not going to consider where this is undefined because it makes no sense in the context of the problem. But we are going to find out where the numerator is equal to 0. And that will be where, if you watch the algebra here, you'll see it. Marginal cost equals average cost. Gives us places to look for a minimum cost. Y'all follow? So this now makes sense to you? Average cost equals marginal cost is a place to look for minimizing our average cost. We good? You understand what's going on here? Okay, I hope so. Let's look at example 6. It says, suppose the cost is just what it was before. I erased it. Can somebody tell me again? C of X, hang on. X cubed.
Minus 6x squared.
Good.
Plus 15x.
Okay, so that's our cost. It's the same as it was before. I guess he doesn't want to get too creative, I guess. X represents, it's in thousands of units again. Is there a production level that minimizes average cost? If so, what is it? Finding the derivative, finding this part of it won't be very hard because it's a polynomial. C prime of X is what? 3x squared minus 6x, no, 12x,
Well,
12x plus 15, right? But I need to set it equal to C of x over x. Well, C of x over x looks like this. Which is what?
It's squared minus 6x plus 15.
Correct. So that, I'm gonna say 3x squared minus 12x plus 15. That's my marginal cost. It's gonna equal average cost by dividing by x. I get this, x squared minus 6x plus 15 again. And so now I need to figure out what the value of x is that makes this true. And so I need to get everything over on one side, preferably where the square term is positive, which would be this side. So it would be 2x squared. Negative 12 plus 6 is negative 6. 15s are out. So now I can factor. Got our x equals 0 anyway.
Yep.
Which is dumb. So it's going to be 3. 3 what? 3,000. 3,000 items will minimize your cost. So now you've got to have a discussion in your board meeting about how you're going to maximize your profit and minimize your cost and find the place, the production level that's going to do those the very best. And that's in a very, very simplistic situation. So the question is, who comes up with this stuff? Who comes up with cost functions that are actually viable for a company? Actuaries do.
Yep.
And they are close to God. That's true. They run it out. I would say God. Actuaries. If you like economics and you like math, actuaries are a great job. It's not very well touted out there. We had somebody go into actuarial sciences, a couple of people from actual calculus class, only because they started looking into it, said, yeah, that's something I like to do. Very stable job, pays big money, because people that understand the math and can do these things for companies and actually make them profitable, they pay big money. Steady work. Okay, good job. Okay, I've done that example. There's just one more little tiny blurb at the bottom of page 225. Most of you will find this to be a stupid discussion, what I'm about to tell you, but some of you who have the absolute heart of a mathematician may find value in this. So I'm going to read it anyway, just in case you have to be one of those people. And this is really funny how he phrases this. In case you're wondering how we can use differentiable functions like C of x and R of x to describe the cost and revenue that comes from producing a number of items that can only be an integer. In other words, the items are countable that you produce, and yet we put them on curves where the x-axis, which is the number we produce, is not in nice discrete little packets. You can have a 2.4 and a 7.87 and stuff like that because they're smooth. If you're wondering how we can possibly do that, then listen. When x is large production level, we can reasonably fit the cost and revenue data with smooth curves, C and R, that are defined not only at integer values of x, but at the values in between, just as we do when we use regression equations. So we're just going to connect them. Connect it up. Once we have these differentiable functions, which are supposed to behave like the real cost and revenue when x is an integer, we can apply the calculus to draw conclusions about their values. We then translate these mathematical conclusions into inferences about the real world that we hope will have predicted value. When they do, as in the case with economic theory here, 2 pieces of economic theory we discussed, we say that the functions give a good model of reality. But they are not reality because they are not integers, they are continuous. What do we do when our calculus tells us that the best production level is a value of x that isn't an integer, as happened in example 5? We use the nearest convenient integer. For x equals 3.414 thousand units, by an example 5 we use 3414, or perhaps 3410, or perhaps 3420 if we ship in boxes of 10. We just give you a region to look for, right? Even though the answers were irrational, it doesn't bother economists. It bothers mathematicians sometimes. They want the absolute maximum. They say, wait, I did this. No, you gotta get back to the real world and these estimates around that number. All right, turn page, there you are. Jeff, start on the dark blue exercises. He suffered a couple of times by starting with it. Okay. Especially if they're on different pages. If they're on the same page, it's pretty easy to tell where to go. I was just teasing him. But see, if they have the quick review and then the exercises start on the next page and you tell them all and you turn the page and go, you did that to me a couple times. What? All right. So get after it and, I'll probably give you tomorrow and maybe even Monday to work on this. These are hard.
These are hard.
Expect them to be hard, but don't shy away from them. Get them done.